All right, so today we're gonna continue our discussion of non-abelian gauge theories. We're gonna be discussing confinement. Are there any questions from lecture 14? If there are questions, ask them as I review what we discussed in the last lecture, as usual. All right, so in lecture 14, we discussed asymptotic freedom in non-abelian gauge theories. Basically, this was the first example. We practiced first examples of genuinely interacting quantum field theories in 4 dimensions using non-abelian gauge theories that were asymptotically free. We saw that the beta function we calculated would end up being negative asymptotically free if you had few enough fermions for your non-abelian gauge group. So we're going to discuss that today. I'm going to start reviewing it up. So here's the Lagrangian, the Fediev-Popov Lagrangian for non-abelian gauge theory. This is the kinetic, this is the standard Yang-Mills non-abelian gauge theory term. Charge fermions coupled to these gauge fields. There's a gauge fixing term. There's a ghost anti-ghost term that had to do with exponentiation of the determinant that popped out of the change of the variables in non-abelian gauge theories. This was our covariant derivative. There's a coupling inside the covariant derivative, the gauge coupling. And this is a representation of fermions. We often take them to be fundamental, anti-fundamental, and the representation for the gauge group here, we've taken them to be adjoint for gauge fields so that this is a carriage, right? Okay. Asymptotic freedom was the statement that beta function of these of the gauge coupling in these gauge series end up from some range of variables becoming negative. Good. To do this calculation at one loop, we discussed the diagrams we have to consider our gauge boson self-energy, which is picking up four Feynman diagrams contribute. This was the only Feynman diagram with an NF multiplying it that was leading to a screening effect. And these are the contribution coming from pure gauge bosons, and we said that it will lead to anti-screening. So to get negative beta function or asymptotic freedom, there will be competition between these two sets of terms. There is a fermion self-energy. The only diagram that contributes to it is the standard one that's familiar from abelian gauge theory, QED. There was a boson-fermion interaction where we had this new diagram next to the diagram we calculated before. And then the counter terms are very similar in spirit. Good. Is this part clear? We calculate the beta function at one loop. The structure of it was very similar to QED. There was a delta 1, delta 2, delta 3 as before. In renormalized perturbation theory, we calculated in terms of the scale dependence of counter terms, the coefficient of the counter terms. And they were basically fixed by representation theory. We saw that you could write the beta function as minus g cubed over 4 pi squared. 11 over 3 of C2 of G. G is the adjoint group. Minus 4 over 3 NFT of R. So if we're in fundamental, anti-fundamental representation, what is T of R? T of half. What is C2 of G for gauge group SUN? N. Right. So for SUN gauge theory with fundamental and fundamental fermions, this would be 11 over 3n minus 2 over 3 NF. Right? So for example, in the case of QCD, what would be the N? 3. So you would get 11 minus 2 over 3 NF. Well, okay, I'll like. So if NF is small enough, you get asymptotic freedom, right? Okay. So we explained this in terms of charge screening. Almost, I don't know, I was kind of sick last lecture. I was incoherent at the end of it, so I'm going to repeat the argument. So charge screening in QED is the following effect, that you have a charge. So there's 1 over R squared field and 1 over R potential that it causes. This is the electric field. Then quantum effects could be just qualitatively described in terms of fermion, anti-fermion, electron positron pair creation. And in this in this background field, they will form dipoles. So in the vacuum of QED is like a dielectric material. So when you apply electric field to it, these dipoles will be aligning in the opposite direction, and the net result, because the net result would be that they would screen the electric charge, right? We calculate the contribution of one loop to how this screening happens, and we discussed the form of the coupling, QED's coupling as a function of scale. We talked about Landau pole and all that. Now, there's charge anti-screening in non-abelian gauge theories due to the effect of gauge self-interaction. So I went through this last time, but I made just the last step I did not finish. So let's go through that now. You have, for simplicity's sake, you have SU2 gauge theory. And you have a charge rho 1, which will create some background gauge field, which is E1. Whoops, right? These are my equations that I have to solve. It will create an E1. We said that this E1, because I did not put on any rho 3, this E1 would act as if there's negative rho 3, right? So there would be, it would act like as if there's negative rho 3 here. So there will be, this negative rho 3 will have E3 corresponding to it, like in these directions, inwards. Now, if your A2 is in this direction, here you have A2, and E3. You're going to pick up a contribution to E1 from here, which looks like, whoops, sorry, signs are flipped. So the contribution that you pick up from here, because A2 is aligned with E3, is like a negative charge, rho 1 charge. Here they're anti-aligned, it's like positive charge. So the net effect is like a dipole, but in the same direction as the original charge. Now you might say, oh, what if I flip A2, just repeat the argument, the dipole is still facing outward. The sign of A2 does not matter. As a matter of fact, it won't matter which direction A2 is facing, because this dot product will always project it to the following argument, the argument I presented. All right, so it is a phenomenon that is due to the self-interact, the gauge transformations, or the form of the interaction, that the dipoles resulting from vacuum fluctuations of non-abelian gauge theory will be aligned with the charge, which means that due to the quantum effects, the charge will effectively grow. Right? Good. Questions? Okay. So last time I started this, but we ran out of time. What we're going to do quickly today is we're going to use the background gauge field method to rederive the beta function of non-abelian gauge theory. and establish very clearly that the beta functions depend only on representation theories, just like a very representation. At one loop, the calculation is just completely representation theoretic. So what was the background field method? You take a mu and you expand it around some classical value, a bar. We said that it's convenient to define covariant derivative with respect to the background gauge field. Why? Because we're going to calculate the effective action of a bar, right? Now, effective action of a bar will have a residual gauge transformation. It will have to, right? And that gauge transform if you package everything in terms of covariant derivatives with respect to this background gauge field, things are a lot more obvious, right? Yeah. We did that, right? So we defined this covariant derivatives as a background gauge field. So we expanded everything in this form. All the bars mean that except for this side bar, it means that they're background gauge field. So there's F mu nu bar, right? All right, actually, I went through these. We have a lot to discuss, so let me go a little bit faster. No, let me just present this. So here's the Lagrangian, right? So the term that is the standard F mu nu squared term will give you the curvature term or the background field term. These will be the background curvature, background covariant derivatives, which is for the fluctuating fields, and then FABC, of course, will appear for fluctuating fields. Here's a gauge fixing term with respect to the covariant, background covariant derivative. It's convenient here to use a gauge fixing method or choice, which is in terms of the background covariant gauge. But you could always redefine, reshuffle things. So to calculate the effective action, what we did was in background field methods, we took the field, expanded around the classical value, looked at the action up to the second order of the fluctuating field. Now the background value appears in the kinetic term or the coefficient of the Gaussian term for the fluctuating field, right? And that was at one loop a determinant, right? Log of that determinant was the thing that was a big part of our effective action. This is familiar. Am I going fast? Okay. So here we do that. We just take the second order term. Of course, there are interactions, but it won't matter for one loop effective action. You just write down everything. Use integration by parts. Write down everything in terms of the background A mu. Sorry, in terms of the fluctuating A mu field, M mu and N mu fields, right? Of course, these terms are clearly, we're coming from some interactions, but the part of those interactions that were background now just appear as coefficients in the Gaussian. The same way that when we did when we took the OM model, right, we expanded around a particular background gauge field, right? The interaction terms, well, the background value contributed as some sort of mass term. Anyway, you remember that. Okay, then what we did was that we focused first on the A mu. Something that's really neat is that using using this like the generator of Lorentz transformation for 4 vectors, you could rewrite these L2 terms in an elegant form in this way. This TG of BAC is just, these are the representation matrices in the adjoint, which means FABC, right? You could do the same thing for psi bar psi, right? And you rewrite everything in this form. So the point of this calculation is that you see that the contribution coming from that second order A will take the form of minus d bar squared eta mu nu minus 2 half f bar of b da da da. This is the generator Lorentz transformation for 4-vector, and this is just fixed point representation theory. Same here. When you do this for the spin half, you get a very similar expression. This is the Lorentz generator for spin half field. This tells you that it's easy, convenient to define the following differential operator, which is for representation R of internal degrees of freedom and spin J. This is what the object is. This is the Lorentz generator for spin J. Written in this way, then the effective action, which was this guy expanded to the one loop, could be written in the following form. Actually, maybe I just put the that here. So there will be the part that's coming from the background value of the action. Now, the rest of it will be these determinants for 3 types of modes. What are the degrees of freedom in my problem? I have the gauge field transforming in adjoint, spin 1. This is minus half because it's bosonic. I have fermions. Oops. I have fermions that are spin 1. This is spin 1. Spin half, and they're transforming representation R. This is NF over half because they're fermion, they're anti-commuting. There are NF of them, right? Positive means they're anti-commuting. And then I'm going to have the ghost, which is delta G0, Lorentz scalar, but adjoint. And this plus has to do with their anti-commuting, right? So let me just first say it, look at this expression. So my effective action, my effective action is gonna look like this. It's gonna be the usual action for the background gauge field minus half log of determinant of this differential operator for the for the fluctuating gauge field, NF, I think I was using capital N here, F over 2 for the fluctuating matter fields, right? Fermions. And here's the fluctuations of the ghosts, right? All right, so this is my effective action. Good. Now, let's say I've calculated my effective action. Recall what the Wilsonian framework was. In the Wilsonian framework, what we had was that we had effective action renormalized at some integrated up to some cutoff lambda that took the following form, right? Where the coupling depended on lambda, right? As you change the cutoff, the form of this part remains the same. It's just the coupling that changes in the following way, right? So this suggests that in comparison to the Wilsonian framework, this coefficient should also become this thing should also become a coefficient multiplied by this term, right? If I can repackage this contribution as a coefficient multiplied by this, I can read off an expression like this, which is my beta function, right? So if log determinant of delta Rj is expanded to the lowest order, is integral d4 of 1 over 4 f mu nu bar a squared with some coefficient Crj, right? These coefficients Crj's are the things that I will keep track of, right? Say it this way. Yeah, that's right. Then this term contributes with a coefficient like this, right? So the first term has 1 over g squared, right? There's 4. This term will contribute as actually, this term will contribute half CG1. This term will contribute minus CG0. This term will contribute NF over 2 CR half. right? Now, going back here, if this is now, if I've identified this expression, next thing I know is that these coefficients should also have a dependence of the form log of m squared over q squared. Or lambda squared over m squared, depending on how you define things, right? And this coefficient is the thing that goes into the beta function. All right, putting everything together, you could read off the beta function for non-abelian gauge theory. It becomes half c tilde g1 minus c tilde g0 minus nf c tilde of r and half. And how do you calculate these coefficients? How do you calculate these coefficients? Well, these coefficients come from writing log of determinant of this guy in this form. But this was also, it had a very sharp definition, right? It was just this differential operator expanded. So we could just do this calculation once and forever, right? Here's the answer. This C tilde, I think I meant. The C tilde Rj is of the form T of R over 4 pi squared times third for scalars minus 8 over 3 and for Dirac spinors minus 20 over 3 for 4 vectors. This is the J dependence and this is the R dependence. Right? So it's all kinematics. It's all fixed. Let's put all of them together. The beta function, you just put them in, the numbers, you add them up. You get minus g cubed over 4 pi squared, 11 over 3, C2 of G, minus 4 over 3, and Ft of R. That's another way of deriving the same equation. So to repeat, what did we do? We used background field method, right? We introduced a background gauge field, right? We took our gauge field, wrote the background plus fluctuation. We performed the path integral up to the second order fluctuating field. It gave us the effective action, which was the action on the background gauge fields plus a bunch of log determinants. Log determinants of a bunch of operators. Those were just fixed by representation theory, right? We calculate those coefficients and the result, this is all one loop calculation. It's very important, right? It's only the one loop that gives you these log determinants. This is the answer. Good? Any questions? So for example, in the strong nuclear force, quantum chromodynamics, G is SU3, Tn is half for fundamental, anti-fundamental, and then you get this beta. You get this beta function, which is negative or smaller than.
How many NF typically exist?
Are you talking about standard particle physics? What is an F? Flavors of firmament. Yeah. Well, we'll discuss this in standard world. All right. Any questions? So this was just something I wanted to calculate last time. We ran out of time. It's another way of calculating the beta function of non-abelian gauge theory. So what is that? We saw that in QED, we had the Landau pole in the UV, so well, at some high energies. Now, when the theory has negative beta function, the coupling grows in the infrared. There could be a Landau pole in the infrared, right? The coupling can go to infinity at some scale. So here's some, for example, some form of a beta function of the type we looked at, right? So it's minus g cubed over 4 pi squared b, so b some positive number. And alpha squared is g2 over 4 pi. This is the solution. And you have a Landau pole at this energy scale, at some infrared scale. Right? What does that mean? What's the meaning of this Landau pole? For example, for QCD. It means that at some low energy, sorry, yes, at some long distance scale, the theory is strongly coupled. Right? So perturbation theory must break down. If you want to understand the long distance behavior of QCD, we need to take strong coupling into account. Another way of saying this is that we are surrounded by strongly coupled physics. It was obvious it had to be. It had to be. We're looking for a genuinely interacting theory, right? All right. So in the yeah.
Must we have a lambda pole?
Hmm?
Like if you don't have lambda pole in the UV, must we have it in the IR if it's
So you see, Landau pole is at this level of arguments, yes. Landau pole is not a physical problem. It's something that your perturbation theory naively tells you that it's growing. So you could go to the next order in perturbation theory. You could go to the fourth order or fifth order. You'll still get a Landau pole, and you just keep correcting it. But what that physically means is that the coupling is going to grow. You're going to step outside the perturbation theory. Right? So there's some other physics. That physics being in the UV is bad, right? Because that requires fine tuning. You're missing some physics. Well, it just means that your theory is fundamentally effective. It cannot be the whole story. But it being in the IR, it's okay. QCD in the UV is very simple. But in the infrared, it's hard. Yep. Now that we actually found examples of four-dimensional genuinely interacting quantum field theories, we're faced with another problem. What is the physics of these theories in the IR, right? Because perturbation theory breaks down. What are we going to say? So today, for that, we're going to wait until part 2 of this semester, which is about non-perturbative methods. Well, I'm not going to say much about that, but today, in the remainder of this lecture, we're going to discuss some non-perturbative physics special to non-abelian gauge theories in the infrared, which is very, very crucial. All right. In particular, I'm going to describe what we think happens in the infrared of non-abelian gauge theories. So when G goes to infinity at some energy scale, what does it mean? What does it say? We have the action. Sorry. We had the action. G goes to infinity, the action becomes 0. All right? What does that tell you in the path integral? This action was the weight of the path integral for different field configurations. When the coupling was small, it was saying that you have a classical solution and the coupling was controlling how much fluctuation, the size of the fluctuations on top of this. When the coupling goes to infinity, all fluctuations are equally likely, right? So it's just, you just drop the action from your integral, right? So integral of dA mu of e to the power of is mu dot 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 is integral of a mu. Everything is equally likely. We'll see that if your A mu is SUN gauge fields, which means unitary matrices, these are hard random integrals, right? Well, we're going to discuss that in the remainder of the course, but the theory, we think at this, in this limit of G going to infinity, shows confinement. It undergoes a phase transition called confinement. And the confinement, we're going to describe it in the infrared. Okay? And we're going to try to derive it, like argue for it based on lattice gauge theory. That's what we're going to do for the remainder of the course. The lecture. Yeah.
Quick question. If all the field configurations become equally right, then doesn't my theory become extremely complicated in the infrared?
Of course.
So what is the solution? Non-perturbative?
Something non-perturbative. That's what we're gonna argue. Well, it's going to be something complicated, right? But we're gonna try to argue using lattice gauge theory, which is a non-perturbative formulation of the theory, for a phenomenon we're going to describe in called confinement. It's one aspect of what happens in the IR. Okay, good. So I'm going to define what confinement is. Any other questions? We say a gauge theory is confining if all finite energy states that are invariant under a global gauge transformation. So, for example, QED is not confining. Why? Because it has a state with finite energy, which includes a single electron. A single electron state under a gauge transformation, psi of x going to e to the power I alpha psi of x, and it's global, meaning they everywhere, is not remain invariant. Does not stay invariant, right? It's a charged state. A theory that's confining cannot have any finite energy charged states. Is that clear by definition? Good. So one particular implication of this is that a single excitation of charged matter in this. So what are we describing? We're describing non-abelian gauge theory coupled to charged matter, right? We're saying that every single charged matter excitation should be infinite energy. What are non-charged excitations on top of vacuum? What are what are charge zero excitations on top of vacuum? Can you give me an example? Like in QED. Oh, sure, but like,
I mean, like positive.
exactly. Q minus Q, right? But this is not gauge invariant. So what's the excitation? What's a gauge invariant object? Just connect them with a Wilson line. I'll remind you of this. Part one of the course, we said that if you take a Wilson line and attach a charge here and here, that object is gauge invariant. This is a gauge invariant operator in QED that acts on the vacuum and it creates the charge neutral state. Right? So what this means is that in non-confining theories, these type of states are the only things you can have. Right? So this should have significantly less energy than a single Q. So it would be tempting to say less separate. Okay. Good, is that good? So the theory is not trivial, right? This is the definition of a confining theory for this course. So if isolated charges have infinite energy, all excitations should be of this type, roughly speaking, right? So the fact that this should be finite energy and this configuration should be it's tempting to say, let's take this and separate them and just pull them apart until this flux line snaps, right? Then you have separated and turned them into two separate charge states. That, in confining theories, requires infinite energy. Actually, said a little bit easier. I don't have to even like say infinite energy. As I stretch this, there will be a moment where it's energetically favorable for this to snap into this. right? So it's energetically favorable at some energy scale for this to happen. This is a physics of confinement. So you're not going to be able to find an isolated charge, quark. If you are in the confining phase, right?
When does confinement case like happen?
I've not described it yet. Deep in the IR, the theory will be confining because the coupling grows. In the UV, the theory will not be confining. And there will be scale where confinement, deconfinement transition occurs.
Do we know what that is?
Yeah, there's a long discussion. Well, you mean experimental? Do we know what that? Yes, lambda QCD. It's called lambda QCD. And for QCD, it's called lambda QCD. All right. So is confinement clear? This is what we expect in the infrared. That's what we see in nature. In nature, we have a theory called QCD. Look around, we do not see single quarks. All we see is hadrons and mesons and things of that type, right? These are all configurations with several quarks, but no individual quarks.
But isn't it a proton a combination of three quarks?
Yeah, we're going to describe that in the. Yeah. The point is that there should be charge neutral is all that matters.
Yeah, protons are not charged neutral, right?
With charge. So yes, it is.
Oh, it does it like
Oh yeah. That's why we're going to describe the Sanomol particle. The Sanomol, the group is SU3 times SU2 times U1. You have to say each excitation, what are the charges, you construct the representation, take these objects out of them, blah, blah, blah. Right? If the universe was just a bunch of charged, non-abelian, like charged particles that were some particles that were charged under non-abelian gauge theory, that was all that you had, then you would get only mesons. These are called mesons, right? Quark antiquark. Good. All right. We're good. Now, what we're going to do in the remainder of this lecture is to argue using, so this is the very first time we're going to do non-perturbative stuff. Using a lattice gauge theory, we're going to argue for confinement. But of course, I'm not going to have time to do the whole thing, so you're going to have a homework, which is related to this. All right. In non-abelian gauge theory, there are charge neutral observables. These are Wilson loops. Trace of a Wilson loop in non-abelian gauge theory is a gauge invariant non-local observable, right? So trace of P, this is path ordered, has to be path ordered. 2 pi of I integral over some loop gamma a mu the x mu. This a mu is Lie algebra value, blah, blah, blah. You know that stuff. All right. So here's what I'm going to say. I'm going to relate this state, Q plus Q minus, this charge neutral state, to a Wilson loop where this is time, Euclidean time, and this is space. This is capital T. This is like a Wilson loop that's square. It goes in the spatial direction for R, Euclidean time for T, back here, back here. What is the interpretation of this? The interpretation of this is preparing the state. So if I cut it here, if I cut this path integral here, that's like preparing this state, Q minus Q. This bit of it is like e to minus capital T times H Euclidean involving this thing, and then this part of it is the overlap with Q minus Q. So this Wilson loop, this Wilson loop in the Euclidean theory could be interpreted this way. If capital T, this time, is much larger than R, this is basically e to minus t, the energy of the pair, because this is Hamiltonian, right? It tells you how just that energy of this pair. So if I want to get, if I calculate the 1-point function of the Wilson loop in the Euclidean theory, Euclidean spacetime, that gives me a sense of the energy of this bound state, this pair, quark antiquark. Yeah.
Why the condition T much larger than R if this? To me, when T is very large, it is very small.
When T is very large, what is?
The exponential minus T stuff is very small, and then
Yeah. Well, that. If this Q minus Q was an exact energy eigenstate, right? Then this would literally be E minus capital T E pair, right? It's not an exact energy eigenstate, so you'll have to put in there E to minus T expanded in energy eigenstates, and in the limit of T capital T being very, very large, you still get an expression of this type. That's the origin of it.
This with a gap spectrum.
Say it again.
So you need a gap spectrum for this or
Gap spectrum of.
no Q minus Q.
You're asking whether so okay, E of pair will be a function of capital R. You're asking whether this energy goes to what do you mean by gap here?
So well, is it a continuous spectrum?
As a function of capital R? What is it?
So what I was thinking is that you say e to the minus P E pair when like the spectrum is discrete. So you sort of if P is very, very large compared to R, then that sort of makes sense. If you have a continuous patch, then you should sort of have an integral around.
Very good. Yeah, very good. We're gonna see that. So yeah, I think I'm gonna calculate this and we're gonna see what happens. It's not real. The word is not gap, but yeah, you'll see that. If I do not address, if the calculation does not address this, asking for you. Okay. In fact, the expectation value of the Wilson loop is an order parameter, or like a maybe order parameter is the wrong word for it, but it's the it could be used to detect the deconfinement phase transition. Now, here's how it's going to behave. Above when it's not confined, when it's deconfined, right? Above the confinement-deconfinement transition, when it's deconfined, the energy of the pair as a function of R is going to look like throughout the guess. Think about pair. Sorry?
I was asking you so we're talking about the deconfirmation.
Yeah, deconfined.
So one over R.
Yeah, exactly. Alpha over R. right? And then in that picture, it's clear that if you just separate, you could separate them to infinity, and then that requires finite resolution, right? So this is the behavior that you expect when the theory is has free charge, finite energy charges. Below, this will actually lead to something that's called perimeter law. Okay, I don't need to spell. In the Wilson loop, the value of the Wilson loop will be proportional to this perimeter, this length. Now, below the transition, when the theory is confined, we're going to find a potential that's linear in R. So it grows, right? And that would correspond to a volume law. So the value of the Wilson loop will be proportional to the area. Sorry, I said volume, the area law. So that's how this Wilson loop could be used to. Is it clear why area law? Look at this E pair. If E pair is proportional to R, what is TR? Area. All right. So I'm gonna use a very super dirty trick to calculate the this 1-point function and the free theory in QED. It's a very, very dirty trick. This is the path integral I have to calculate, right? I'm gonna think of integral over gamma of dx mu as j mu as a source. Complete the square, and this could be turned into a rigorous thing. But if you recall, when we did these calculations of this sort, the result comes out as jj delta mu nu, right? That was the source path integral, Gaussian path integral in the presence of source. Here you get e to minus half g squared integral of gamma dx mu integral of gamma dx nu delta mu nu minus 1. This is a propagator. QED, what is a propagator? It's just 1 over k squared. You do these integrals, you get delta mu over 4 pi x minus y squared. This is Euclidean, right? Is it clear why this is 2? Think about it. All right, you're going to do the calculation. You guys, I trust you can integrate over this guy, integrate with this kernel over this circle loop. The answer, well, this is a double integral. Of course, there's a particular relation. There will be a part that comes from the contact terms where x and y sit very, very near each other. That will give you UV divergent term, 4 epsilon over epsilon UV cutoff, plus 2 pi over r times t. This is the result of the calculation. Just a simple integral to do. And this is the reason for large t. Somebody was asking. The reason for large t. ln of t. Corrections. So the 1-point function of W of gamma basically takes the following form. E to minus 2 alpha over pi epsilon mu nu minus epsilon r. This term is going to be interpreted as the E of the pair, energy of the pair. There is a piece to it, which is UV divergent. This is the divergent self-energy of it. And then there is a Coulomb potential type. Good. All right. So this was the Gaussian theory. This was the simple theory, QED. In non-abelian gauge theory, there are interactions and we have to expand in powers of G. The theory is no longer free, it's interacting, but it doesn't matter. You could expand it, you could expand the exponential. The very first few terms, the first term is exactly the same as like what you would have gotten in QED, except that there's just these TAs in front. That gives you another representation theory factor. Otherwise, the structure is the same. So conceptually, the structure is the same. But the calculation would be done reversely. All right. Is this part of the calculation clear? There's no surprise here. You're just above the confinement transition. The theory is perturbative. We're actually even considering the free part of it, right? The tree level part, not free, tree level part. And there's this alpha over R potential that you see. Now, below the transition, we're gonna be trying to do this calculation of the 1-point function of T gamma mu at infinite coupling. First, you gotta let go of the path integral. You don't know how to make sense of it. It's infinite coupling. The only other thing that we have is the lattice gauge theory. So we're gonna try to use lattice gauge theory. Do you guys remember what lattice gauge theory was? I'm gonna review it. So actually, let's pause here. Are there any questions? So is it clear what we're trying to accomplish? We're gonna try to use lattice gauge theory to argue that at infinite coupling, V of R is proportional to R. That's what we're doing. Which will be some sort of a qualitative argument for confinement. So what was lattice gauge theory? Lattice gauge theory, we brought this up in part 1 of the course as where do gauge theories come from? We said that, well, you start with putting degrees of, with the lattice, you put degrees of freedom on each side, you could put degrees of freedom on, if you could put degrees of freedom, well, okay, sorry. Let's put a degree of freedom that is a unitary matrix at each point. You're gonna have these Wilson loops, Wilson lines that connect them. Right? It's a function of y and x. They go from x to y. Under gauge transformation, they transform like u of y, u dagger of x. This is what it means to say, if you attach a charge q here and minus q here, this is gauge invariant. Because w in the middle transforms like u dagger. Well, there's a direction, right? Good. Then we take this Wilson loop and expand it. On the lattice, we can expand it and get for nearby points, and we get the Lie algebra valued gauge field connection. Right? So this A mu is now Lie algebra valued in SUN. To model this, and part 1 of the course, we said, let's start with lattice. On each point, we're gonna put a degree of freedom that belongs to SUN, gauge group G, right? And because we want to associate this to a Wilson loop infinitesimally, right? There will be a point and a direction. You could think of it as a degree of freedom sitting on the link. Right? So I'm going to label it by point X and a vector alpha. Or if you wish, this is a mu, it's related to a mu of X, right? The mu tells you which direction. X is here. Is that part clear? All right, so these are SUN matrices. We said that if I have a plaquette, I can go around the plaquette like a cell, a minimal cell, and write down the following Wilson loop, right? It's just B, B dagger, B, B dagger, B dagger, right? So this is what it is. It's just a plaquette. gauge invariant. Yeah, their emission conjugate. Right? Now, how is this plaquette different with the same plaquette, but with the opposite direction? Where you go in the other direction. That's where every B is replaced by B minus 1. Minus that plaquette. Right? It's different. So if you have a plaquette, you take this plaquette action and or Wilson loop and add to it the minus plaquette, the reverse orientation, you could expand it in small epsilon. Small epsilon, we said this in the part 1 of the course as well. You get G squared epsilon 4 trace of F12 squared. This is direction 1, this is direction 2. And this F12 comes out as the non-abelian curvature. So if you take your action, minus 1 over 2 G squared, sum over all plaquettes of W plaquette, including both orientations, in the small epsilon limit, the continuum limit, you're going to get the non-abelian Yang-Mills, non-abelian gauge reaction. Right? This F mu nu squared. Trace of it. Yeah.
Here, the coupling G is finite.
Mhm.
Okay. But we're not saying it needs to be small or large. Or anything.
Not yet. That's on my next step.
Yeah.
What?
Why did we have information conjugate?
Oh, because I'm going to write my action and sum over these double plaquettes. Right. I just want to, because I'm going to write it, like I'm going to put it e to the power of ISH. E to the power of IS over H bar. Yeah. Well, depends. If depends what there's so much, you can answer that in so many levels. You could think of it as building a Hamiltonian out of this. You could talk about the action. It's about the action being real. You definitely don't want a complex action. All right. So I just reviewed what we did in part 1 of the course to argue for the emergence of non-abelian gauge theory in the infrared of sublattice normals. I said I reviewed this to say, well, we did all this. Now let's take the G going to infinity limit. In the G going to infinity limit, S goes to infinity, right? S goes to S goes to 0, and all configurations are equally likely. So your path integral will be a path integral over du's, but now this is all possible u's. Now on a lattice, it's pretty clear what the path integral is. It's a path integral over lengths. It's a product of overall lengths of a bunch of Haar random unitary integrals. Right? To each link, we associate an n by n unitary matrix degree of freedom. We're gonna multiply. We're gonna multiply for every. We're gonna include an integral for every link. Right? Of a Haar random unitary. Does everyone know what a Haar random unitary is? Who doesn't know what a Haar random? Who knows what Haar? Can someone give a definition of a Haar random? So SUN is a group manifold. It's a manifold, right? Think of it as like this. It's not SUN, but think of it as something like this. Haar measure is a volume measure on this, which is uniform. which is left and right invariant. Right? It means that if I take a function and integrate it in one way or another, like if the group acts on it naturally by moving points around, and under left action and right action, this volume form is invariant. Right? It's just a volume form, but it's the most natural uniform volume form you can write down. It's called Haar random. So do read up on this.
Where does the random part come? Hard that you define a hard measure here, but where's the random part come?
Every measure is a random variable.
Oh, okay, got it. I get very far.
Right? A measure is a positive.
Yeah.
So an integral of a Haar random unitary is 0. These are things you can play with. Anyway, if these don't make sense, your homework will make more sense. You will do this in your homework. So at infinite coupling or large coupling, you're going to calculate this using Haar random integrals. And the result is going to come out at the following: 1 over g squared area, which is r times t for this rectangle, over epsilon of uv squared. And if you view this as an e pair times t, you learn that e pair is proportional to r. That's linear potential between non-abelian point charges. So it takes infinite energy to separate charges. Charges are confined. This is a really, really like physicist-y argument for confinement. For better or worse, it's one of the best we've got. We don't really know how to make sense of confinement. It's like an open problem, and it's a Millennium Prize problem. We don't really know how to make sense of it mathematically rigorously, right? Because mathematically rigorously, the theory exists. We know it exists, right? But to argue for confinement is a really hard thing. This argument was very lattice, right? But we see confinement in nature. So we'd like to explain it. Questions?
Could you please go back?
Down,
No,
up.
yeah, so we had that RMP program. How did we get the, oh, that's the only.
Sorry, say it again.
No, I was asking, how did we get the last one? I think that's something.
Yeah, so this 1 point function is e to minus e per t, right? The area is RT, therefore the e pair should be proportional to, well, the truth of it is that there's a coefficient here that depends on geometry, right? Blah, blah, blah. Was that your question? Yeah.
Actually, my question was how did we get the first expression?
Oh, that's your homework.
Yeah, right.
That's your homework. You will know that very, very well soon. You'll explain it to me, actually. All right. I think as physicists, you guys should learn Haar random integrals and Haar random measures. They are extremely important concept. It's an important concept in physics. A random state. What is a random state? Classical random state, you know what it is. Quantum random state, a good meaning of it would be Haar random, because it lives in some subspace, a Hilbert space. The only notion of random is to apply a random unitary to it. With what measure? With what P of U? The uniform P of U. Right?
Why the uniform?
There was well, that's a very, very good question. There is, in classical physics, we talk about uniform probability distributions in thermodynamics, and we give it a name. What's it called? Yeah, but like what principle do we call it? Equipartition. Right? Where does it come from? Just minimal knowledge. If you don't have any other information about the system, the fair assumption is just take it to be uniform. Unless you have further information. It's like there are a million ways of arguing for it. My favorite way is Bayesian. Just you don't know about it, take it to be uniform. Because everything else implies knowledge. Okay, very good. So let me summarize. Are there any questions?
Yeah, so okay, so we have some scale at which confinement happens, maybe start with a couple of theories.
Mhm.
Is is this a sharp transition? Like what happens around lambda QC?
Those are very, very good questions, extremely hard questions. And
I mean, can we probe lambda QCD with like current energy scales?
theoretically or experimentally?
experimentally.
Oh, yeah, absolutely. Absolutely. What is lambda QC? What's the phase transition? Okay, one of you guys should tell like I don't know, we don't have time for presentations. But next time one of you guys tell me what the lambda QC, the energy scale is. I can tell you now, but you go read about it. There's an energy scale. Yes, we could probe it experimentally. The physics of it is very interesting. Yes. The problem is that theoretically it's hard to calculate. Physics over there is very difficult. Confinement, deconfinement transition. Well, okay, I'll let me just summarize this and we'll all go offline and I'll talk about confinement. All right, so in summary, what did we do today? We reviewed that we used background gauge field methods to come up with another way of deriving the one loop beta function of non-abelian gauge theories. And that derivation made it very clear that it's just basically representation theoretic. Right? It's very representation theoretic. We defined this differential operator, which was log of determinant of it. This differential operator only depended on the spin and this representation spin and the inner representation under the gauge group and on the background gauge field. Then log of determinant of it ended up being proportional to the kinetic term or F mu nu bar squared, right? The standard the Yang-Mills term for the background gauge field. The coefficient of it, we used the part that was log of lambda over m to calculate the beta function. They just directly went to the calculation of beta function, but those coefficients are completely fixed by representation theory. I just coded what those numbers are. For scaling, it was like -3, blah blah blah. So the moral of that is that the one loop beta function of gauge theory coupled to matter is just you tell me what representation, how many of this field, how many of that field. I just add them up, you get a beta function. So you can cook up things that one loop are gauging there, are asymptotically free. Good. Then we turn it around and we talked about, okay, so now the theory exists, but then we have another problem. In the infrared, it grows, so we can't solve it. It just gets really, really large. And we live in the infrared of QCD, and actually there is, at some point, it becomes strongly coupled. And even though our calculational methods stop, we still have understanding of the physics because we can perform experiments, right? So we see confinement. Confinement is an experimental observation. We observe that confinement, that fundamental degrees of freedom of Q's charged matter is not there. It's not found like as individual quarks are not found in nature, right? And also the potential, well, I haven't discussed it, but the potential R behavior is very, very crucial. We argued for that using the infinite coupling limit of lattice gauge theory. So that was a confinement. So this story of confinement, deconfinement is a long, long story. Any questions? With this, we're going to put an end to discussion of non-abelian gauge theories. Probably I'll spend 2 lectures on spontaneous symmetry breaking of gauge theories. before going on to standard model, where we get to those our questions you're asking. So I was planning on doing some QCD here, but I'm gonna put all the QCD in standard. It's better to do them at once, yes, full story lesson. The only thing I haven't quite decided is that whether I'm gonna be desperately needing anomalies or not. So for now, I'm just postponing anomalies to after standard model, because it's non-perturbable. All right, any last questions? All right, so let me just talk a little bit